Good morning to all of you. Today we are going to discuss the Maxwell equation. Let us see what is the importance of Maxwell equation. So basically the Maxwell equation are the basis for the electromagnetic theory. So Maxwell has proposed four equations for us. Four equations. So out of these four equations, these are the basis for the electromagnetic theory. So unless we have these four equations, we cannot be able to analyze the propagation of electromagnetic signal in the free space. So out of these four equations, two are the steady state equations and two are the time variable equations. So these equations are the vector based equations. Basically we are having two types of quantities, one is a scalar, one is vector. Vector here in this sense, like the signal is going to change both in the magnitude and direction. Example like speed. So we are going to calculate the speed in terms of like distance per hour. The speed we are going per hour per time like that. Whereas if you take a scalar quantity like mass, weight, that's all. It is not going to change with respect to the time. So we can analyze the Maxwell equation by means of the vector quantities. So let us see how this Maxwell has proposed four vector equations from the steady state equations. Let us start with the displacement current. So here we are making use of two quantities. One is the curl, which is indicated by cross mark. One more is the divergence. Also, this notation is dot. The first step is we are going to take curl H is equal J bar. Curl H bar is equal J bar. Here H is the magnetic field intensity and J is the current density. So the density which is not varying with respect to the time. It's only the current density which is available. So if I take divergence of this curl, so on the both sides I will get divergence of curl of H bar is equal to divergence of J bar. So but we know that divergence of curl H bar is equal to 0. So on the RHS we are having divergence of J. So divergence of J bar is equal to 0. But we know that from the continuation of equity, like this one is equal to the minus dou rho by dou t. This rho is nothing but volume charge density. So finally the equation is taking the form of like minus of dou rho by dou t is equals to 0. This equation is a steady state equation. Now let's see how the Maxwell suggested the vector quantities for these equations. Yes. So we can see here the Maxwell actually we are having curl H bar is equals to J bar. This is a basic equation we have used in the steady state condition. Now we are going to use like a J bar plus J dash bar. So this dash indicates the displacement, means it is going to vary with the time. The current is going to vary with the time. Here there is no variation with respect to the time. It's only the current constant. Here it is going to vary with the time. Now so I do the same procedure. I am going to take the divergence on the both sides. So I will get here divergence of J by J bar plus J dash bar, and here you are having curl of H bar. Same procedure we follow here also. So finally we are going to get here, as we know that this one is equal to 0 LHS. So finally divergence of J bar plus divergence of J bar dash is equal to 0. From the continuity of equation we know that divergence of J bar is minus dou by dou t rho, this is the volume charge density. So plus divergence of J bar dash is equals to 0. So I may take this minus dou by dou t rho on the RHS. I may get divergence of J bar is equals to minus of dou rho by dou t. So this is the fifth equation like it is. But from the Gauss law we know that del dot, that is the del divergence D. D here is nothing but the electric field displacement, or we can also call it as electric flux density. So del the divergence d bar is equals to volume charge density. So we substitute this value in this equation. So we are going to get. So we are going to get here divergence of j bar is equals to divergence of dou by dou t into d bar. So finally we got here j dash is equals to dou of d by dou t. So we are having here, but curl h is equal, we are having j plus j bar dash. So we got j dash is equals to dou by dou t into d bar. This is the flux density. So these are electric flux we are having. These are Maxwell third equation. Like this, Maxwell for every steady state equation changes to the time varying equation. So totally like that he proposed two time varying equations. So this is the equation. Finally we can write this one as del curl h bar is equals to j bar plus dou by dou t d bar. So these are Maxwell third equation. Like that we can able to build up the remaining equations. So we may see the four equations of Maxwell. Let me explain you the four equations. So this is the first equation. So del divergence D is equals to rho. This is the Maxwell first equation, and del divergence B is equal to 0. This is the Maxwell second equation, and del curl E bar is equal minus dou by dou t B bar. This is the Maxwell third equation, and del curl H bar is equals to J plus dou by dou t is the Maxwell fourth equation. So like that Maxwell proposed four equations, and the first equation is called as like a Gauss law of electrostatics, and second equation is called as Gauss law of magnetostatics, and third equation is called as the fourth equation, the third equation. So fourth equation is called as Faraday's laws of induction motion, and the third equation is called as Ampere's law. So like that we are having the four equations, and we go one by one. Before that, let us see what are these parameters. So D is the electric flux density or electric displacement. The units are centimeter by centimeter square. And rho is as I told before, volume charge density or free charge density. The units are per centimeter cube. And B is the magnetic flux density, or we can also say that this one magnetic induction Web per meter square, or we can use the units Tesla. So E is the electric field intensity or electric intensity, units are volt per meter, and H is the magnetic field intensity, units are ampere per meter. And finally J is the current density in ampere per meter square. So these are the parameters we are going to use in our Maxwell equations. Yes. So here we can see the four equations. The first one is, as I told, Maxwell del dot d bar is equals to this. What it is telling the equation, describing. So first of all, it is a time independent equation. So as I told before, we are having four equations. 1 and 2 are the time independent, 3 and 4 are the time dependent. So what is this statement is showing? So here del dot is divergence. Del divergence of d bar is equals to the rho, that is the volume charge density. How to explain this one is, for example, what the statement is equation is stating is like this. For example, I am having a closed surface. The amount of electric flux or the force which is coming out of electric force coming out of this closed surface, let the surface is S. So the force which is coming out of this closed surface is d bar, is equals to the total charge within the surface. That is the Maxwell first equation. This is also called as Gauss law of electrostatics. Gauss law of electrostatics. That's what it is mentioned here. Second one is the del divergence dot b bar is equals to 0. You know what is this? So here we are saying that in a closed surface, whatever the charge is developing is equal to the total electric force which is going out of the closed surface. Similarly, here the Maxwell second equation, del dot B bar is equals to 0. This bold indicates the bar, a vector quantity. So this is also time independent equation. So what it is stating is, you don't have any beginning point or ending point for a magnetic loop. If I take any closed surface S, let it is a closed surface S, and we are going to discuss in terms of magnetic field. There we are discussing the first equation in terms of electric. The second equation we are going to discuss in terms of magnetic. What it is stating is, the amount of the magnetic field developed around a loop is equals to 0. Any closed loop, the magnetic field is equals to 0. This is the second law. So this is the third equation and fourth equation of the Maxwell. You can see here, third equation is del curl E bar is equals to minus dou B bar by dou T. So what is it stating here? So I am going to take here like the amount of the variation of electric field with respect to the magnetic field. What will happen to the magnetic field when you vary the electric field? What will happen to the electric field when you vary the magnetic field? This is known as Faraday's laws of induction motor. So there is nothing but Faraday's laws of electromagnetic induction, and this negative sign here indicates the Lenz's law. We call this one as justifying the law called as Lenz's law, the negative sign. The fourth equation is a Maxwell fourth equation. So already we derived this equation before. Del curl H bar is equal to J plus dou D by dou T. So these are the four Maxwell equations which are very important for our propagation of electromagnetic signal in the free space. So you can see here, this is a magnetic force which we are going to enclose in the electric closed loop. So what is happening here is, whenever we are going to, you can see here, so when the magnetic field is going, magnetic forces we are sending inside the electric loop, closed loop, so we can see the variation of the electric field. That's what it is. Del curl H bar is equals to this one, is equals to J bar plus dou by D by dou B by dou T. This is the third equation, and this is the last one is the fourth equation. Around the closed loop, the magnetic field is equals to, that is the del curl B bar is equals to minus of dou B by dou T. Okay, thank you.